Okay, we will start the lecture. So today we are going to study about the unbalanced three-phase system. You know me, right? So here a small diagram has been given here in the front cover. Actually, this is what we are going. This is the theme of our discussion. This diagram, actually, this is the theme of our discussion. So once we study this part, you will understand what kind of diagram it is. So you know this kind of diagrams we call three-phase phasor diagram, the phasor diagrams of those three phases. And you can see there are some sequence components. Here you can see 1A, 1B and 1C, and you can see 2A, 2C and 2B, right? 2A, 2B and 2C and 2B, right? So ABC sequence, this is one positive sequence, and you can see here this is negative sequence, because you know this is ACB. You know that this kind of sequence we call positive sequence and negative sequence. This kind of wording you know already from the last lecture. So here this part is normally known to be the zero sequence you will study. So if you add all of them, you can have your UA, the U1A and U2A, and the U0A. U1A is actually the positive sequence component of A phase, and 2A is the negative sequence component of B phase, and this is zero sequence components. If you add all of them together, you will get UA, and similarly you can get UB, something like that, and you see something like this. So actually if it is unbalanced system, so UA cannot be equal to UB as well as UC, as well as the phasor angle between them could not be equal to 120 degrees. In that concept, so these unbalanced phases can be split into three different balanced system. Okay, we will see, that is our theme of our discussion. So this is a kind of introduction for before beginning the lecture. Okay, anyways, we will move on. Okay, so we will see the causes of the three-phase unbalanced system. What are the causes to be unbalanced, and what are the effects because of this unbalanced system? So you know that the causes of unbalanced system is because of the source unbalanced or load unbalanced. Further, because of that load or source unbalance, the line voltages and the line current would be not equal to 0 to each other, and it will not be equal to 120 degree phase angle shift from each other. So there would be a neutral current returning through the neutral conductor. So let's say that is equal to IN, and that is equal to IA plus IBB plus ICC. Further, the phase, if you add phase voltages, it could be 0, it could not be 0. Anyways, the phase angle between them never going to be 120 degrees. Further, anyways, VAB plus VBC and VCA is equal to 0. It's a rotation, right? It's in a rotation. VAB is equal to VA minus VB, and VBC equal to VB minus VC, and VCA is equal to VC minus VA. And if you add all of them together, it will gives you the 0 value. So then it gives you you can construct a triangle like that using the line voltages, and you can draw VA, VB, VC just like this using the neutral point. Right. So this is how it will come. If it is balanced system, this triangle will be this triangle. Which kind of triangle? The equilateral triangle, as well as the neutral will be placed at the gravity of that triangle, gravity point of that triangle. Right, and VA and VB, VC are equal to each other, in between them, that is equal to 120 degrees. Okay, so again it's repeated. So In is in this way. In is equal to Ia, Ib, Ic. It could be equal to 0 if there is no neutral connection in the load. It is equal to 0 to, it would be anything. So but Ia, Ib, Ic couldn't be placed in 120 degrees. Similarly, Va, Vb, Vc also could be equal to 0 or could not be equal to 0 for unbalanced load, and never going to be 120 degree spaced from each other. Further, the Vab, Vbc, Vca always that is equal to 0, that you know, because same rotation. So Va minus Vb minus plus Vb minus Vc, Vb minus Vc plus Vc minus Va. So if you add off all of them, it comes 0. So in that way, so these are the set of equations we get. We move on. So if you take these kind of things, we will analyze using the sequential component method, or you can say symmetrical components, for which to analyze the unbalanced three-phase system. The key idea of symmetrical component analysis is to decompose the unbalanced system into three different sequences of balanced network. The network are coupled only at the point of unbalance. This is the key idea of these kind of techniques. So as I said, it is unsymmetrical. So unsymmetrical, that's mean unbalanced system is going to be decomposed as balanced component and the symmetrical components in this way: the positive sequence and the negative sequence and zero sequence. Let's say the pointed arrow in the red here and the yellow here and this blue here are the unbalanced voltage. So this unbalanced voltage is going to be decoupled or splitted into balanced positive sequence and negative sequence, zero sequence. You see, these are the ABC voltages. A plus is in this way and B plus will be in this way, and that is 120 degree placed from the A plus, and C plus is here. Then the sequence is ABC for clockwise rotation, right? So if it is clockwise rotating, if you are keeping your eyes here, so A, B, C, and the negative sequence A mine. Okay, here this C mine, that is here A mine and the C mine and B mine. So you can see this is negative sequence. The sequence comes ACB pattern, right? So this is negative sequence. These negative sequences are equal in magnitude, 120 degree placed each other. And you see the zero sequence. Zero sequence are in this manner, is equal in magnitude as well as phase angle. A0 and the B0, C0 are the same direction it gets. So if you can decompose into three different elements, you can have these ABC things, right? So as you said, let's say ABC are three different unknowns. So with another three different unknowns, we can elaborate ABC. This is the main implication behind this model. Alright, here you see the assuming the three unbalanced voltage phases are VA, VB, VC, having the positive sequence ABC, and using the symmetrical components, it is possible to represent each phase of voltages as VA equal to VA0 plus VA plus and VA minus. So here similarly VB and VC can be represented as below. So here VA0, VB0, V0 VC0 are zero sequence component. Those are equal in magnitude as well as phase angle. And A plus and B plus C plus are the positive sequence. Those are placed in 120 degree balanced, each 120 degrees each other, and all of them are equal to the same value. And VA minus VC minus VB minus, it is negative sequence actually, because the sequence is ACB as we discussed in the earlier slide, and VA minus VB minus VC minus are the negative sequence, right? But all of these A minus B minus C minus are equal to same phase angle, sorry, with same magnitude and the different 120 degree phase angle difference. But VA0, VA plus and VA minus, similarly VB0 and V plus V minus, VC0 plus VC plus and C minus should will not be equal to each other. Okay, in detail we can see. So these are the VA plus B plus C plus are positive sequence, and the VA minus B minus VC minus are negative sequence. VA0, VB0, VC0 are positive sequence. It's an exemplary diagram, phase diagram is given here as in the picture. So these are three phases, right, each equal in magnitude and displaced by 120 degrees, having the same sequence as A, B, C. That is actually we are discussing about positive sequence. And the negative sequence, you see, it is equal to A, C, B. The zero sequence are in this way, right? So here another example has been given here. So this VC equal to 0. That means there is no voltage at the C terminal. Let's say one phase is earthed and VA and VB phases will be there. This system can be, it is actually unbalanced. So it can be splitted into three different sequence component. Those are zero sequence and positive sequence, negative sequence. So these are given here, and the resultant phase diagram is given the left side, right side of the sequence diagram, as you see here. So this is the synthesis unsymmetrical phases using the symmetrical components, right? Similarly, we can represent current values. IA equal to IA is A0, zero sequence, plus IA plus IA minus, and IB equal to, that's when B phase current is equal to IB0 plus IB plus B minus, IC equal to IC0 plus IC plus IC minus. Okay, now we will convert the sequence into phase values, phase, then at that time you can have an equation. So only three of the sequence are identical. So if you know these three of the sequence, you can determine if you know the IA0 plus I0 comma IA plus and IA minus, you can determine for B, that is IB0, IB plus and IB minus, and IC0, IC plus and IC minus. So you can determine these values. So if you know IA0 comma IA plus and IA minus. So let's say that IA0 is equal to I0 and IA plus equal to I plus, and IA minus equal to I minus. Okay, let's have in this way. So the others are determined as follows. So you know that alpha equal to 120 degree, then alpha plus alpha squared plus alpha cube equal to 0. Since you know that alpha cube is equal to 1, alpha plus alpha squared is equal to -1. if you add both of them, that equal to 0, right. So by definitions, you know that IA 0, IB 0, IC 0, all of them are equal to each other. So let's have IA 0, IB 0, IC 0 are equal to I 0. Similarly, the positive and the negative sequence IB plus, that means minus 120 degree, then alpha squared into IA plus. So you can write alpha squared into I plus, and the IB minus equal to, that is plus 120 degree placed from the IA minus. So the alpha into I minus. Similarly, IC plus is equal to 120 degree placed from the this one, then alpha into I A plus, right. So IC minus is equal to minus 120 degree placed from the IA minus. So I squared into I minus, right. So we can by assigning this value, we will have an equation in next slide. Okay, then the three phase unbalanced current is equal to IA, IB, I0. You can write in this way: I0 into 111 and I plus into 1 alpha squared into alpha, then I minus equal to 1 alpha alpha squared, because that is negative sequence and that is becomes alpha alpha squared. So you can have this equation in matrix form. So similarly, you can write this equation for the our unbalanced voltage phases in this way. So here, defining the A as equal to this component 111, then alpha squared alpha 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 squared. So you can have this equation: I is equal to A into Is, and we can have V equal to A into Vs. So Is is equal to A inverse Ip, Vs is equal to A inverse into Vp. Then A inverse is equal to 1 over 3 into 111 1 alpha alpha squared 1 alpha squared alpha. So if you here A is equal to just normal A. So if you want to work out, so you just try with MATLAB, or if you want to work out, you can try home. Okay, you can submit it by next week. Before next Wednesday. Yes, before next Wednesday means next Wednesday means 3rd of December. So please submit it before 3rd of December. All right. Okay, it is an example given here. So this is an unbalanced system. So to determine the balanced system, so you can do this one. So this so determine the sequence component. So you can have this kind of equation, and you can calculate V0, V plus, V minus, right. So this is a question of find the symmetrical component, that means symmetric sequence component of unbalanced system. Voltages A, B, C respectively. These are the voltages. Okay, right. So it's been calculated. V0 is equal to this much and V plus equal to that much. V minus is equal to 0.558 162.6 degrees. So now here we will see the star connected unbalanced load, right. So you know that you can write equation, we are going to say unbalanced load. So we know this kind of equation: IA is equal to VAN YA, IB is equal to VB and YB, and IC is equal to VC and YC, right. That is normally using the Ohm's law. You can write these equations. So here YA, YB, YC are admittance respectively to A, B, C phases of that load. Since there is no neutral wire, since there is no neutral wire, the neutral current is 0. Anyways, that current IA, IB, IC can't be equal to each other, as well as it will not be placed 120 degree to each other. right. So using this equation you can substitute the 1, 2, 3 equations in that. So you will get VAN into YA plus VBN into YB plus VCN into YC, that is equal to 0, right. Similarly you can write an equation. So VAN can be splitted as VA minus VN. So here VA is the source voltage with respect to the O terminal. So let's say there is the earth terminal, right? The O terminal is earth, right, in the source. So you can see this is the VA, right. So VAN is difference between the ZA and VBN is difference between ZB, and the VCN is difference between the voltage difference between VCN. So you can write this equation VA into YA plus VB into YB plus YC into VC into YC minus VN YA YB YC. So you can determine the neutral voltage respective to O terminal. So the VN is equal to VA YA and plus VB YB plus VC YC over YA YB YC. If the load is balanced supply, then VA VB VC are placed in 120 degree to each other. So if it as well as VA VB VC are equal to the same magnitude, then you can write this equation Vn is equal to YA plus alpha squared YB plus alpha YC YA YB YC. So this is the N. So here you can see in the triangle. So here with respect to this ABC terminal, so you can construct this kind of triangle using the line voltages, and we use with that line voltages are the phase voltages are respect to this O terminal. Then OA, OC, OB, OA, OB, OC are the phase voltages of the source, and with respect to that point the neutral voltage is VNO, right. This is the shift. Because of that, then VAN, VCN, VBN are the voltages, right. Voltages of the each arm of the star connected unbalanced load. This is the neutral shift from that thing. So it gives you unbalanced system. Similarly, you see if it is connected to the neutral impedance, so the equations comes in this way. Only this y, because this In will not be equal to In will not be equal to In will not be equal to 0, then In is equal to Vn Yn. So using that part, so you can have this equation. So this Yn terms is added here. Let's say y that's Yn, Zn is infinity, that Yn becomes 0. So this Yn disappears in that manner. So if it is balanced supply, these terms comes here. Similarly, the construction of this triangle and the neutral shift also will be there. Okay, so you see, so if the neutral impedance is not there, so you know O and N are the same location, and the VA VB is according to the VA VB VC. If it is balanced, it would be an equilateral triangle. If it is not balanced, it will not be an equilateral triangle. It would be a different triangle, and the current value can't be equal to 0 because the ZA, ZB, ZC are not equal to each other. So In value can't be equal to 0. So you can have these kind of equations, and VBN and VAN, VAN is equal to VA, VBN is equal to VB, and VCN is equal to VC. And the neutral current you may calculate, and there is no voltage VON, and VON is 0, right. That means that here you see in the previous equation that yn becomes infinity, and yn becomes infinity, in becomes 0. That is, sorry, not yn, because vn becomes 0. So if it is actually balanced one, you may calculate using the equation balanced load. You may calculate using this equation va equal to va into ya alpha square yb plus alpha into yc. In we calculate. Right. If it is delta connected load, right. So you see, if it is delta connected load, so you may construct the VA, VB, VC, VA, BB, BC, VCA, that is always equal to 0, right. So if it is balanced only, the triangle will be equilateral triangle. So there, if there is any artificial neutral, with that artificial neutral we can determine the neutral shift, right, in this picture. Right. So these are the respective equations are given here. So IA, IB, IC, IEC is equal to 0, as well as not necessarily to have 120 degree apart from each other. But VA, VB, VC always equal to 0, and VA, VB, VC are given here. Right. So power associated with the unbalanced system. So with the phase components for single phase, so you know that for the single phase you may have this kind of equation, and for the three phase unbalanced system you have to multiply the voltage, phase voltage value as well as phase current value, in the conjugate of the phase current value. Then S3 phase is equal to VA into IA star and VB into IB star and VC into IC star. Then you can calculate the complex power of the three phase power. So using the real part, if you can add up those things, you can have the active power, that's means power consumed by the load, can be calculated using the real part of this complex power. And otherwise, if it is single phase, you know how to calculate the consuming power, that is pi p pi, it's given as vi into cos theta, but here you will do in that way. So see, with this abstraction of that knowledge, you can use these equations VA, VB, VC into IB, IA, IB, IC conjugate, right. You know that this is 1 into 3 and 3, this is 3 into 1. So the VP is actually the transpose of that voltage vector, and voltage vector means 3 different set of values, right. So IP is 3 for that, there is no transpose, transpose is this is something like here. So here you see that you can substitute for VP as A into ES, and similarly IP A into IS. So if you do so, you can end up with this equation that VT VST vector and IS and VAA here, right. So if you take the transpose, so you know that VS come in front and the AT come behind. So it is how the transpose work, right. So VST and AT A conjugate. So you know that A conjugate is equal to 3 into A inverse. So you can take the 3 front and A inverse cut off. Then if you can multiply the sequence components between the between them, so you will if you multiply by 3, you will get the complex power as it is in the equation, right. So these are some tutorial questions. So you just try the tutorial and submit it before the next week as with the assignment. Right. Earlier one is not a big assignment, you may try and submit it. And this question 2, this is also tutorial questions, it will not be counted, but anyways the instructor would be discussing with you. Anyways, before that you must make the submission, then only sometime it would be counted by the instructor if there is any loss of marks because of the attendance failure, so it would be counted. Right, question 3 and the question 4, question 5. So please submit this question, so as answers of these questions. So next we will see the sequence impedance for the load 1. That means we will see a load something like that. So here you know that In is equal to Ia plus Ib/Ic, and VAG, that means the voltage between the terminal A to the ground terminal, that is equal to current into the impedance multiplications as it is given here, right? And if it is so, you can say that VA for this In, you can write Ia, Ib, Ic, right? So if it is so, you can have the equation VAG, VBG, VCG, and as in the picture, as in the slide. So VAG, VBG, VCG can be given as a vector form, and the impedance matrix could be given as a matrix forms as here. So you see this one, these are the phase voltages and the phase current and the impedance relationship as it is here. So if we are going to convert into sequence component, you can calculate the sequence component of this load also. It is actually balanced load, right? So if it is so, you know that V equal to Z into I, then you know V is equal to A into Vs, I equal to A into Is. A Vs is equal to Z into A Is then, right? So if you take the inverse A, if you multiply A inverse both sides, so you will get Vs equal to A inverse Z A into Is. If you do this kind of multiplication, you know that A inverse and the A. So if you do that multiplication, you will end up with this matrix, right? So you may try this one at home. So if you are interested, you may try this one at home. There are multiple material, so you can try this one at home. So further, all right. So this is the final the vector voltage vector sequence. What is it? Sequence component vector, and the vector for the current and the voltage, sequence component matrix for the impedance. So if you decouple this matrix into different equations, you will end up with this zero sequence equations and the positive sequence equation and the negative sequence equations. So using that equation, you can construct different circuits for that load. So these are the zero sequence network of that load and the positive sequence network of the load and negative sequence of that load, as it in the purple diagram over there, purple colored diagram over there, right? Similarly, so we can have some important note. So you know that if is in the zero sequence network, only the neutral impedance gives you the greater impact with as a series 3 times of the neutral impedance. So if the neutral impedance is infinity, means if the load is ungrounded, so there is no zero sequence current flowing through the network, then V0 is equal to something like that, there is no neutral current flowing through the network, right? This abstraction can be extended up to the generators, just like that, but you will just like in the picture, the same network, if it is a balanced generator, same network comes in this way. If it is a balanced 3-phase network, same networks come in this way, but the generators normally generates the positive sequence voltages. So if it is so, you will get the positive sequence. If you will get the voltage source and the positive sequence network as it is in the picture, as well as according to the load only the zero sequence or positive or negative sequence current flows, right? So if it is balanced system, this I0 current also would not be there, and the I negative current also would not be there. That means negative and the zero sequence currents will not be there, and positive sequence network only be presented. So these are the system actually in the balanced network. Normally we were discussing only the positive sequence network. So that two other networks are disappeared, but if it is unbalanced system, these two other networks with the positive sequence networks would come into the picture. Right, sequence impedance in general, right? So you see you can model uh, any load or source lines into sequence component network. So we will see in general picture. So you know that the phase voltages vector is equal to phase voltages impedance phase impedances matrix into current vector, current phase current vector, right? So you know that Vp, that's been phase voltage vector, can be written into A into Vs vector, and the Ip vector can be written into A into Is vector. So the equation comes in this way, right? If you multiply A inverse both sides, you will end up with this equation. So you can say that the Vs equal to Zs into Is. So here Zs is equal to A inverse into Zp into A. So it can be written in this way: 1 over 3 into A conjugate Zp into A. Then Zp is equal to, similarly, A into A is A inverse. So it can be written into 1 over 3 into A Zs into A conjugate. So it is normally, if you know the phase impedance matrix, you can calculate the sequence impedance matrix as it is in the picture. Okay, this is another assignment. So the assignment 7, or it also has to be submitted by 3rd of December or 10th of December. Assignment 7 could be submitted on 10th of December. So just try this part. That means you have to calculate it's actually balanced load, balanced line system. So you may calculate the sequence impedance using the techniques what we studied, and you can write on the Z0, Z plus, Z minus as here, right? Z0 is equal to Zs into minus 2 Zm, and Z plus is equal to Z plus is equal to Zs, and the Z minus is equal to also Zs, it seems, right? So you may try and calculate that part. Z, yeah. So you I'm not sure about that value. If you calculate it, you will get the answer. So I didn't calculate, so you just do the calculation and submit this assignment before 10th of December. Right. Further, so we will analyze imbalanced load and sequential components, right? So here you see a 3-phase source and 3-phase line, and there is a single phase load on the A phase line only. So actually it is an imbalanced load, right? So if it is so, we should calculate that imbalance sequential component, and the IA current, IB current, and the IB current will be 0, IC current also will be 0. It's an imbalanced load. We must calculate it. So how the calculation could be done? So we will see that part. Right. Right. Okay. Here Zm is mutual impedance between line. Okay. And Zs is series impedance of the line. Right. So here for the generator, you can write since it's a 3-phase source, for the generator you can write the 0 sequence and the negative sequence, positive sequence and negative sequence components. So similarly you can write for the line the 0 sequence and the positive and negative sequence components, right? So if you write in this way, so we'll get this answer. You have modeled your system, and you have to model your load, right? So for that, right, you know that IB equal to 0 and the IC also equal to 0. VA is equal to IA into Z. Yes, VA is equal to IA into Z. So this you have to add the Z in line with the sequence network. You should find the sequence component or effective component on the sequence network. Okay, right. Right. So similar again, it's been given IB is equal to 0, IC is equal to 0, V is equal to IA into Z. Right. Here you can say, you can write this equation. So IS is equal to A inverse matrix into I phase vector, right? So you know, in the I phase vector, the IC components are 0, IA component only will be there. Then if from that equation you can determine the sequence component. IA is equal to IA 0 is equal to IA plus, and the IA minus equal, that's also equal to both of them, and IA by 3. The sequence component are 1/3 of the phase current of IA, right? You know that IA is equal to VA over Z, then IA 0 is equal to VA over 3Z. Okay. Right. Similarly, you know that VA is equal to VA 0 plus VB 0, VA 0 plus VA 0 A plus, and the VA minus, right? So you know that IA, from that earlier equation you have IA 0 equal to VA into 3Z. So if you convert this VA into sequence component, so you can determine the sequence network, right? IAC, then if you can substitute for that VA in terms of sequence component, then you will end up with VA 0 plus VA plus VA minus over 3ZF. So you can say that these sequence networks are connected to each other with the 3 times of Z matrix. So here it is something like that, 3 times of Z. This is the this is the effective sequence network, and you may calculate. So here IA, IB, IC, so IA plus IA minus component are same. So using this equation you can determine the IA current, right, as it is in the picture, right? So using that equation you may determine, this is the, using this network you can determine IA plus, using this IA plus or IA 0 or IA minus you can determine IA. This is how we will do our question, right? So if it is unbalanced load, what's happening here? So these sequence networks are interconnected to each other, right? So we will do I am giving you a small assignment, so that's mean assignment 8. So in that one, so you can determine the sequence component and how it's being interconnected between the sequence network. Okay, thank you very much. So I'll give you assignment. Actually, I'll give you assignment with in the next slide. Right. Okay, then I thought of giving you as an assignment this question, but so let's try as a tutorial question number 6. You should find the impedance matrix and try to find out the sequential voltage, sequential current using the sequential impedance matrix, the phase current using the sequential component, complex power using the sequential voltage and currents. Check your answers. It's tutorial number question 1. Actually, these are exact questions in the tutorial number 1. So check your answers. All right. So these are the things to deliver in my plate, from my plate. So please try to understand, try to study from it. Okay, this is the end. Thank you very much for listening. Okay.